So thank you so much. I see that lots of people are coming in here. It seems to be that there is a huge interest in optimization of data workloads by partitioning. And this is something, what is a cool feature, what I want to introduce, not introduce to you, but show you how partitioning can make your life so much easier as you will never expect. Again, first of all, a big thank you to all the sponsors of this super conference here. I think that you all know that without the sponsors, these kind of big events could never ever happen. If you want to replay everything what I do, what I will demo here, because this is a very heavy demo-based presentation, just only a few slides for you to understand the workload, but then we go step by step through the T-SQL code and we do the measures, whether it's good or not. So if you want to replay this, you can follow these links for this session. Most important is for you the last one. This is the bit.ly partitioning for data management. If you follow this link, you will get all the example codes, the demos, and this presentation, what you see here actually on the screen. The databases I'm working with is the ERP demo database, which is a big one, and the customer orders, which is a smaller one. That all depends on how long normally this session will go. I will play around with the customer orders database, which is approximately 500 megabytes in size. If you want to do that with the big one, with lots of more data, then take the ERP demo database. Only requirement for you for the demo databases is you have to run at least SQL Server 2012. To be honest, I would say that everybody of you is running at minimum this version. So a few words about me. Forget about the commercial on the left side. What is the most important thing? It's my email address. So whenever you have any question concerning this topic or any other topics engine related, feel free to drop me an email to uwe.ricken@db-berater.de. One important hint, you will see here 4 demos. These demos, what I show you here, are all use cases which are coming from real customer scenarios. So I created this session based on my experiences I had with customer projects or customer alerts when they were raising and said, hey, can you help me? We have some problems here. So the customer scenarios, to be honest, have been very much simplified for this session too. But the core concept is that you understand what the problem of this workload is, or what the problem of the workload is. So here is my first use case for partitioning. I do not talk about what partitioning is or how partitioning works. I would expect here that you all know about the core concepts about partitions, partition function, schema, and so on. One word before I go into the use cases. I was quite often talking to customers who were running a SQL Server Standard Edition. And unfortunately, I saw that lots of people were thinking that partitioning is an enterprise feature. So this is just only half of the truth. If you have a SQL Server running before 2016, then yes, they are right. You can use partitioning only as an enterprise feature. But the good thing is that if you're working with SQL Server 2016 or newer versions, the partitioning feature is, for God's sake, a standard edition feature. And this is not really known by every customer. So when I introduced them partitioning, they were quite astonished when I showed them the possibility of this by a standard edition. So partitioning, keep that in mind. You have, for example, in this first demo, a high transactional production system. Maybe if you're working with 2016 and standard edition, maybe you should think about partitioning here. Here comes the first workload. I was called by a customer which was coming from the pharmaceutical company. And this was a quite interesting thing. My customer was not the pharmaceutical company, but was the company who has developed the software. And what happens here is the software is monitoring the production of drugs on various, in this case, what I want to play here, 16 production lines. So what happens here? Think about this. Let's say on the first production line, you have some pills for a medication A, on the second one for medication B, and so on and so on. The core requirement is that every charge must go through a Q&A check. And this quality check needs to be stored in a SQL Server database. What did they do? See this one here. You have here up to 16 machines, and this is the basic infrastructure here. And they have one web service in between the database and the machine data, which is caching the information from every machine. And then the web server is going multi-threaded and pushing the data into the SQL Server database. We have lots of problems here. And one of the biggest problems is that the data on the web service in the queues were growing because SQL Server could not save the data quick enough. And the reason for this is a very simple thing. Like, I want to go back to this slide. You see here this big red X. And when you think about the contention, what I was mentioning, think about this. If you have 16 processes which are heavily hitting your SQL Server, they all want to write into just only one file, and everybody is now dealing with the resource with a so-called exclusive block to write the data into the database. The biggest problem is here, if you have too much processes hitting the same resource, some of them must wait. And they have to wait so long until the previous task will release the lock, and then the next one jumps in. And if you have too much of these requests, then you have a queue which is not cleaning fast enough. So this is one thing, and the latch contention was the problem by the database design. And you might think, what? We are talking about partitioning. What is it about the database design? Well, the key point here is every single machine gets its own machine ID, and then we are storing the data by the machine ID and by the date when the record is stored in the database. But if we have a bad database design, then it might be that too much processes are hitting just data into one machine, and then they will concentrate on the last page of the index. So the machine ID and the increasing value of the date will lead to a contention on the last page of the index. A second thing what came up was that the indexes in the database on this table were severely fragmented because the machine IDs were writing from every single process, they had a different value. So that led to page splits, lots of page splits. And these page splits on top of it, because you have now the latch contention. And then the second thing, what is the fragmentation, the page splits, that will lead to longer running actions. And this on a machine where we were forced to push the data as fast as possible into the system. So what can we do in this case? The optimization is in the way that we will now try to cover that with partitioning. So the demo I want to show you here is that we will create for every same table. We couldn't change the table design. There was no chance. But what we could do then is we could create for every single machine ID a separate partition. And this partition can scale way better than pushing everything into just only one partition. You see this here on the right side. Every single machine here, this is partition for machine number 1, machine number 2, and every single machine gets its own partition, gets its own file or files, more files. Here comes another good part if you partition your system. When you run partitions, let's say the machine number 2 has a way higher transaction number, then scale it by adding multiple files to it that we can write faster into the database files. What we did with this solution was the distribution of the data by machine was that we reduced the page locking duration. We had a better throughput if data files are on different storage. And the fourth thing is that we did not have any more index fragmentation because every machine has its separate partition. Let me show you how this will work in real time. So first step to do that is I create my demo databases, which is the customer orders database where I receive my data from. And I have, again, my demo database where I'm playing around in it. The next thing is that I create 2 X events. The first one is for log escalation, and the second one, you see this here, the number 12, that creates an X event, what I need to have. One moment, please. I need to check whether this demo database is number 12. Okay, and then, here it's, okay, it's named. Okay, no problem. Good, so preparations are done. And now we want to speed up our transactional throughput, and here we go. In the first step, I go into my demo database, and you see here my demo table, very, very easy, very simple. I have a machine ID, and I have a timestamp for when the data are pushed into the table, and I have just only for the workload, a fixed length column to force lots of page splits, for example. So we write in total around 1,100 bytes for every single transaction. And this is nearby the same structure as it is with the customer from the size of the row. What we then do is, as it is in the original way, I create a clustered index on the machine ID and the date column. And this is the problem here. Because with this index, we cannot scale. This prevents scaling here. And we get lots of page splits. Because let's say when the machine number 1 is pushing data, and afterward the number 5, it goes automatically after the number 1 rows. But then the third process inserts, let's say, for machine number 3, and that needs to be inserted in between, and we get lots of page splits. Here is just only a simple wrapper store procedure, very simple. I name it send machine data, and it is pushing data into the table. And you see that the only thing what I hand over to this one is the machine ID, nothing else. So then I can have hundreds of thousands of transactions. So now we look for this, that the event for high transactional processes has been started. I did this. Here, this one has been executed. And you see that this one is 110 XE high transactional workloads. This is just only preparation. Let's have a look to this. Go into the extended events, into the sessions. And here, this one is for my high transactional workloads. And you see that the data gets stored in an event file. However, we look into the properties, and what we can see here is that we are looking for ledges when they get released. when they get assigned. Then we want to see the page splits. So whenever a page split occurs, that we can record this. And I want to see the information about, well, what was did we wait for? And we store everything in an event file. In the next step, I clear my wait stats. The wait stats, because here that SQL Server records every single time when SQL Server has to wait for something. And here I now start a very simple process. Let's have a look to this before that you see what's going on. I say I start the workload number 1 with the batch file, and when you look into this, you can see here that I start simultaneously the O-Stress program from Microsoft, and I say, please execute the store procedure, send machine data, where the first process is pushing data with the machine number 1, number 2, number 3, and so on. So in total, we have 16 machines which are pushing data into the table, and every process is pushing 10,000 rows into it. Let me check whether we have on the T drive. This is something, oh, it's there. Okay, so this one gets executed, and I have prepared this, and here we go fast. So now SQL Server is creating 16 processes, and we are pushing data into SQL Server. And you see that it takes a while. So in the meantime, while this is up and running, we want to see what kind of wait stats do we have and what is the highest number of. And what you can see here is SQL Server is running with 94% of just pushing data into the log. That seems to be good, but what concerns me here are 2 points. One of this is the CPU, but this is okay here in my scenario because I just only have 8 cores, but it consumes 16 processes. But look to this, we have page latches here in the game, and this is on way higher in the real production system. And have a look to how long it was taken to push 10,000 data, only 10,000 data into the table. And what you see is it's starting with 24 seconds for the first process, whatever it was, but it goes up slightly. So we have here in the top 25 seconds. And now we want to see what happens here inside, and we go to the analysis. Here is the first thing. The first part is that I want to see, because you remember the page splits, I want to see how much fragmentation do we have, and you see this one here, and this is absolutely a nightmare. So what we see here is that we have 99% of fragmentation. So one moment, yeah. Here I go now for the page splits, and this is what I'm doing here. I'm running a query against this event file here first. And what I want to see is the number of page splits we have here. And look to this. Here you see that we have 21,000 of these page splits. And normally you can talk about a bad page split. That is an indicator that someone has inserted rows in between existing data, is when you have a very high so-called split jump. That means that it not goes directly to the next page, but it has to break a page into 2 parts, of the data of the page into 2 parts, and then move it over to the next free page. So this is very expensive, and it takes you lots of time for the transaction. And here you can see how many latches we had. And let's see this. And you see here where we did have the latches, and you see here that in total it was 67 milliseconds on the index page, 1 millisecond. The average duration is 3 milliseconds on one data. This is, from my point of view, not a good result. We start again this process. We try to make it a little bit better. So what we do then is we want to try to avoid these page splits and the latch contention. And this can be achieved by adding or by separating the data from every single machine, a separate file group and a separate partition. Let's go for this. I truncate the table because I'm not interested in the data inside. And what I'm doing then here is this here. First of all, you see that I'm walking here with a cursor through. Let's see here. I alter my database and I add another file group. And these file groups will be named by the machines, so machine 1, machine 2, and so on. So I do it for 16 machines. First of all, let it run. These are the statements. So I create another file group, and then I add a file to this file group. And now my database is looking like this. First, go here to the tables. You see, from outside, everything is as expected. And this is the good thing with partitioning. It doesn't change your metadata, obviously, for the application. The application, excuse me, does have a table, and you don't see where the data are stored internally. But if you look into the properties of the database and look into the files, you see this one. You see now that for every single machine, I have a dedicated, a logical name. And then you see here that I have a separate data file for every single machine. What you can do here, or I think that you see what can happen here is a very fantastic thing, because when you see that one machine needs to be faster on the storage level, then just move over this file to a faster disk that it can write faster to the database. Good. Next step. Now I'm coming to the partitioning, because this one, what I did here, is not the solution so far. It's just only the infrastructure for the performance boost what we get. What I'm doing now is, when you're dealing with partitioning, I create now my partition function. The partition function defines where the data have to move to. And you see here that it's just only for machine number 1, 2, 3, up to 16. In the last step, I need to have a partition schema. And this partition schema is the glue between the logical abstraction of the partitioning and the physical one. You will see this right after this, because here I will tell the system that, for example, if the number 1, for the machine number 1, the data is going into the table, put it to this partition. Then the next one to this partition, and so on. And here we go with the partitioning. You see that I drop an existing index and I recreate this. And before I do this, let's concentrate on this code. First of all, I drop this, and here's the index. When you create an index on a partition, you define the attributes you want to sort. But then you say, what of these attributes will distribute the data to different partitions. And this one is here my machine ID. So let's see. And here we are. This is my final result. I see that the table machine protocol, this index, is now separated into 16, 17 partitions. Every single partition has its own boundaries. Say everything goes for the machine number 7 goes into the file group, the machine 07, and so on. I clear my performance counters. Then I restart my session, but first of all, delete the former outputs. And then I can again start my transactions here. So I run this, and in the meantime, while I'm running this, have a look to the distribution of data. Go to this. Here is my SQL server. Oh, I have two SQL servers up and running. However, let's see this. Here, this one. Come on. Oh, come on. This is not funny. Ah, here. Perfect. Now you see what happens here. That SQL Server is distributing nearby evenly the data to lots of files. Basically, what happens is, what I see very, very often is that the storage can handle way more data than SQL Server is able to send to the storage. But now, when we do it over multiple files, you can see now that we are pushing the data simultaneously to the different files here. And that makes this one thing very, very fast. So now, okay, this is because here lots of other applications are running on my laptop, but let's see how it increases. So 27, 28, 29. So we have in total a value difference of 1 or 2 seconds. But this is interesting. I want to see what is about the weights here. And you don't see any page latches anymore. The only thing what you see here, and that's way better than it was before, we have over 97% just pure write block. So that means that SQL Server is just only working to push the data into the transaction log. We didn't have to wait on any latches on the data pages itself. And that makes normally the workload way, way faster. So here, let's see how the index is fragmented and see this. Ta-ta! This is pretty perfect because now we have on every single partition an ascending key. That means that we go on every single partition. Let's say the partition number 1 for the machine ID number 1, we have ever increasing dates. So all the data which gets inserted into the partition number 1 are inserted one by one by one by one. And it's single threaded in this way because we only fill it with one process. And that is the reason why we have such a low percentage of fragmentation. So we see it's less than a percent, really perfect. And what I want to see here is how many page splits do we have? You remember my Axe event has recorded this, and then I run this query. I hope that you won't see very much of that, and that's perfect. 7. And this is something where you say, what? That cannot be true. 7 page splits? No. To be honest, we had way more, but what you are seeing here is a page split which was skipping 1 page. So the split jump, if it is higher than 1, we are talking about a back page split. And instead of 21,000 of them, we only have 7 here. So this is the proof of evidence that the workload is way more efficient than it was before. Our transactions are very small now because the number of page splits was not so much as it was before. Second thing is that we didn't have any of the page latches here, or say in other words, we didn't have it in a measurable way. They were less than 1% in total of the whole system. And this makes the workload here very, very efficient. And in total, at this customer side, we had a big, big success with this because we made a benchmark before and after. And what we had here was a performance improvement. It was depending on the number of rows coming from each machine and the size of the rows. But we had an performance improvement of 3 up to 15%. But not only the performance improvement is mandatory here. You know what's another point? It is the index maintenance, because when they run analytic queries against that, they wanted to have indexes which were rebuilt or reorganized. For this table, it was a big, huge table. We didn't have to do that anymore, because whenever we were checking the indexes, we were lower than 1%. And that made it incredibly fast for them. And the daily workloads were way better than before. And the queue never, ever again was increasing so high that we had a big, big queue with thousands of waiting processes. The second one was really interesting. Okay, here it is very hard simplified. The customer is a retail company here in Germany. And one of the biggest issues with them is the following situation. If you go to a supermarket, the good thing with supermarket, what I like here in Germany is they always, really always have fresh things there, fresh bread, fresh milk, all this kind of stuff. How could this happen? And the second question what was coming up for me was, okay, how could this happen? But why or from what did they know how many they have to send to the supermarket? And this is this workload here. So the customer is a retail company, and that loads key figures, so product sales of all cash registers all over Germany. So we are talking here about a big, big, big supplier with over 1,000 supermarkets. And every single cash register downloads its file on an FTP server, then it gets uploaded and pushed into the database every night. So that can create reliable plans for supplying the stores. The key point here is that they have to finish at latest at 2 or 2:30 in the night, because then they need to send out the trucks to deliver the stores to the stores. So that was a quite interesting thing here. What do we have to do? What you see here is a few problems. First thing is, you see the warehouses. So every single column in the background here is a warehouse, and every single warehouse has its different cash registers. So if you look for this one here, for example, the warehouse number 10 had the cash register 1 and 2. Oh, there is a minor problem here. So we have multiple cash registers there. And what they wanted to do is they were pushing the data to an FTP server, and then a bulk load jumps in to push the data then into the database. A parallel processing is not possible because of lock-ins. So if you think about a cash register with 100,000 products entered over the day, and you load it into the database server, what will happen then? You run into a lock escalation, and that means that the whole table gets blocked, and all the other processes needs to wait until the locks are released. This is something what we cannot do. So my demo will not start here with the CSVs. It's not necessary. Think about this. All the CSVs, the cache information, have been loaded into a staging area here. So one by another, everything was formed. So then we import the cache desk data into the cache analysis. And you can see here that we have around about 9 million rows in. And we need to push them by warehouse, by cache desk into the data warehouse. As I said, a very, very simplified thing. We are talking about approximately 9 million rows divided into different warehouses and cache desks. Gosh. So the biggest problem here is that we run it every single time into log escalation. That was exactly their problem. So with every new supermarket they were opening, they had more and more problems to be ready in an appropriate time. So the log escalation prevented data records from being entered into the table. And the second thing is that only when the blocking process releases the log, then we can process the next step. One of the part is, so we've immediately decided to run this on partitioning, but partitioning itself, only partitioning, is not the solution here. And what you have to do is, you have, when you're running with partitioning and you want to prevent log escalation on the table level, then you have to use the log escalation. You have to set the log escalation to auto. But let me show you how this will work. First of all, a few preparations. Here we go. I recreate my demo database. What I'm then doing is I'm preparing a schema staging. Then I do the cache analysis, which is my data warehouse table, the original one, which gets analyzed for filling the trucks. And I have my staging table, the cache activities. So the staging will contain every single item of the cache desk, and the cache analysis then will have a sum up. So what I'm doing now is I'm now filling data into my staging cache activities. This is around 9 million rows. Done. And it looks like this. So I take demo data and I am using them now here for simplification of the product. You see that in my data warehouse number 6, I have the cache desk number 25, and at that day they entered the article dark red for a quantity of 9.47, and the total price was 112. This is just only one single line. And so normally I would say, oh, come on, this is very easy. What we have to do, just only make a sum up about group it by warehouse and cache desk. That's true. But think about this, we want to load in parallel and not waiting till the query is finished. And so therefore, what we are doing now is we are creating a store procedure where we hand over the warehouse. So I create on the staging, on the warehouse and cache desk ID, an index. And this is the distribution of data. Oh, come on, takes a little bit. Okay, this is the distribution of data. You see here, when I run a load of the warehouse number 1 with the cache desk number 1, I have to insert 87,985 rows this is the simulation. And what will happen then? Well, we run into log escalation, and so on. There is no cache desk here, which has less than the magic number of 5,000. So it is clear that we now will run into log escalation. So we go there, and I create my table, which is really a very simple thing, just a one-to-one load here, just to produce high numbers of inserts. I put the index on the warehouse and the cache desk. And then I'm doing this one for monitoring. I create a table called warehouse load. And the only thing what I'm inserting in is, say, give me per warehouse. When did it start? When did it finish? And what is the difference, time difference in milliseconds? And these information get inserted and updated from this store procedure, import cache desk. Very, very, very simple, really simple here. If there is an entry for my for this workload in the table, then skip it, otherwise update it. But what I'm then doing is I'm aggregating the data. I'm pushing the data from the warehouse, from the whole warehouse into the cache analysis. I don't do it with the loop here. And then I update and measure how long did it take. Good. And here I clear again my weight stats, and then I run this workload. This workload number 2, which is the batch here. Let me show you what it does. It's exactly the same. I start my OSTRES on my machine. I'm running this import cache data. And then what I'm doing is load the data for the warehouse 1, 2, 3, 60. And in their scenario, it was around 1,200, 1,300 of these processes running or trying to run simultaneously. But with 16, with my tiny little machine, is absolutely in place. That's okay. So here it goes, it's running, and let me see what's going on in this time. I want to see what is waiting here. And look to this. You see here that we are waiting. Come on, this is from the log here. And you see definitely that we are waiting for page ledges, again, page ledges, but that is clear. But the question is coming up, why is the system not on? Now it's done. It's too less data. However, and this is my wait stat. And most of the time I was waiting for CPU. This is a nightmare, but to be honest, this is coming from the live presentation. In the background, the virtual summit platform is running and some other things. Forget about this, but you see this. This is a mandatory thing. And look to the suspended time. So the time we were waiting for it in total. Keep in mind, I have completely deleted every entry from the wait stats. And now I can see that in total we were waiting 33 seconds total, just only for asking, hey, I want to save data lower in the hierarchy. The indicator, what I have here is that it must be a weight on the table level. The IX is standing for intent exclusive. So I intend to write in a table, and therefore it creates an intent exclusive log. And the average time is over 1 second, and this is incredibly long. And here are my weights, and look to this, and look, that looks really, really funny. My first process was running nearby immediately. So it was, okay. So you can see here that it was taking 2 seconds, but then it drops, it increases dramatically, 11 seconds. Then again, 6 seconds over 17, 18, 17, and so on and so on. So we see here that we have a dramatic increase of the load times. And that was exactly the same behavior with that customer. So what can we do here? Here I see the difference for every single warehouse. This is my warehouse number 1, and you see perfectly, this is under 2 seconds. So my first warehouse, that was the first OSTRES start, and this was taking 2 seconds, but then it was increasing heavily, going, and so on. So that we can say that in average, let's say the median, we have around 17 to 18 seconds our workload, at the time how long the workload did work. And this is way too long. And we had very much differences. You see it here, and the min, the max, and an average 16 seconds. That is too long, especially for this customer. So what can we do here? First of all, I truncate the cache analysis. And let me show now step by step what happens here, that it comes to this extreme differences. I start a transaction and I replay just only the warehouse number 1. So now it starts, done. That was the 2 seconds roundabout. And now let's have a look to the lockings. And look to this. Here is my object. Forget about this. It's because inside the transaction, I want to write when did it start, when did it finish, however. And look to this. SQL Server set an exclusive lock now, an exclusive lock on the table itself. And now think by yourself, what will happen while I am running the warehouse number one? In their scenario, it was taking 5, 6, 7 minutes. And then think about what happens with you. Let's say you are running the warehouse number two. The problem is, oh, sorry, you cannot write data because it is exclusively locked. And now think about 1,000 of these stores where the data, from what we have to load the data into the data warehouse for the analysis of the trucks. Ho, ho, ho. Yeah, this is something what we need to prevent. And here comes the point, partitioning will help you, believe it or not. And as I say, it's just only as a simplification of the whole process. Again, I create now for my demo database, again, multiple file groups, and I create multiple files. So every single file group has its own one. And you see now it's named warehouse, 16 of them, P1 to P16, then the different warehouses. So far, so good. So what we now have is only let's say an infrastructure. So the physical layer of my database, where we do have lots of separate data files. But these data files alone will not help, absolutely will not help to solve this solution, because we have the problem of the lock escalation. Here, I create my partition function. It's exactly the same as it was with the previous demo. In this case, it's called PF warehouses for the function. Then I create the partition schema, which is now going for 16 warehouses. And I now rebuild my table, the cache analysis, and I recreate it and pushing it onto this partitions. This is how it looks now. You see my cache analysis, my index, and you see my different file groups. So everything is now finished, implemented. I reset the performance counters. And I run again the session here, what we had. Go for it. And again, I'm watching what's going on here. That is no more blockings. This is interesting. And see this here. Now they are coming. That looks really curious. You see again, it starts with 176 milliseconds. Oh, what a great thing. But then you see again this increasing dramatically. 7 seconds. Double it to 14 seconds, 15, 16. To be honest, also we have partitioning. Nothing has changed here. And this is because we do not have the problem. We do not have the the lock escalation here, which has been fixed. So let's see. It's not right here, so it didn't take so long that it was in the measurement. But okay, believe me, and I show it to you how it was working. So these are the values: 7 seconds, 13 seconds, 14, 15. So the distribution of the runtime seems to be, let's say, more or better distributed. To be honest, it is. It is better distributed because every single process is pushing data into its own file. But every process, every warehouse had to wait until the lock has been released. So what happens then here is very simple. due to a faster writing, we are releasing the lock earlier, and then we have an average which is 2 seconds lower than before. This is not the way I want to work with this, because that will not solve our problem. And the customer said, well, we had a consultant here who was telling us this will work. And we said immediately, no, it cannot do. It cannot scale. Let's see it in detail. I dropped the cache analysis table. And again, I run my transaction to isolate just only one, to simulate just only one cache test. I run this, go, and then look to the blockings. And you see here, I have in my cache analysis an exclusive lock again. Gosh, it's not working. Huh? So what is the reason here? I roll back, and then on a checkpoint, and here comes the point. To be honest, I cannot understand, I really cannot understand why SQL Server will not automatically, when we recreate indexes or we partition a table, can set the lock escalation to auto. The lock escalation equal to auto. That means when we are dealing with a lock escalation, then SQL Server will not lock the whole table, but only the transaction where you're pushing data into. And this means, hey, come on, we now have a solution, because now when we have 16, in our case, 16 warehouses where data gets pushed into it, then we have a separate exclusive lock just only on the partition level, but not on the table level, and nobody has to wait. So I clear this, and I run, stop, did I do this? Let me check. Just only, okay. So I run the query again, third time, again, the same batch. And then we're going back and seeing what is SQL Server waiting for. Nothing. There is no wait. And here you see that it goes way faster than before. We have 14 seconds in the top. This is due to my limitation, 16 processes, and I'm just running a course here. And let's see what the wait stats are. Again, the scheduler, but here, nothing, nothing, absolutely nothing. Look to the right log. So we were waiting, this scheduler, this is something I need to log manager flush. The write log is the mandatory thing, and we were taking around 4 milliseconds. This is a good thing here. This one sucks a little bit, to be honest, because there is so much pressure on my tiny little notebook. Please apologize for this. So this was an improvement, and I can check this. Here it is, 3 to 14. So in average, we are way better. 14 was the new one, and now we are down to 10. And this is 8 seconds, just only from my demo, 8 seconds faster, and it's nearby the half than before. And what I want to show you here is, again, how this will work now. I truncate my table, begin the transaction. Now I run this, go. And now have a look to what's going on. Look to this. Now we have an intent exclusive lock on the table. Brilliant, absolutely brilliant. Now it works as expected, because an intent exclusive lock is compatible to an intent exclusive lock. What does this mean? Well, all 16 processes, if I could have 16 cores here, would go immediately into the table. All can access the table, but every single process has its own partition. This one here, the hopped heap or B tree. This means this partition is exclusively locked only by this single process. But this is okay because the second one is then going to the next partition and the third one to the next partition and so on and so on. And that's how partitioning can help you scaling your workloads. As I said, I'm really sorry about that. And I'm wondering, why is SQL Server not automatically implementing log escalation to auto when it comes to partitioning? But it is as it is. We have to, that is as it is. We have to accept this. Okay. The third one, let me see what is the time. We have another 15 minutes. I would skip this one here because it's, I wouldn't say identical to the warehouse number one solution, but it is equal to this. Let's come to the, to the management of big databases. And I want to show you something where I improve queries with. Management of big databases. I would say that nowadays we have lots of really big databases. So when I was thinking about a customers, let's say average sizes of databases we had with SQL Server back in 2010, I would say we've been heroes when we were talking about databases which were, let's say, 700 gigabytes. So life was easy as in DBA. It was for one reason easy, because the backup was finished in the night, a restore was in the agreed SLA, everything was okay. But nowadays, starting with big data, with new kind of data analysis, lots of data warehouses, and so on, RE/KI, and so on, more and more data gets used from day to day. I have in other words, the customer with the biggest database I'm supporting here, a data warehouse, is 25 terabytes. To be honest, I've never had a customer with such a big database. But what is the problem? Well, a large company's administrator must recreate indexes and statistics from a 4 terabyte database. This is something what will happen every night. The time window is limited, and a way must be found to limit maintenance to the time window. An index rebuild, for example, that is something what's quite expensive. Or in statistics update, oh my goodness. Furthermore, the SLA determined the downtime of hot data within 60 minutes. If someone of you could restore a 4 terabyte database within 60 minutes, then I would say, yay, respect, good storage. But normally I would say, no, that's not possible. So let's see how you can improve this, how you can do this in a better way. So therefore, what I'm doing is I come first to the first problem is the so-called file group restore. Think about this. Go back to the requirements. You see here that we have only 60 minutes for hot data. I'm playing with small data, but a 15 or 20 terabyte database, to be honest, it cannot be restored within 60 minutes, not possible. But look to this. The management say, well, just please give us at least the hot data within 60 minutes. Hot data does mean from a specific range of data, for let's say for the last 3 months, for example. And this is something where partitioning may help you. Here we go for this. I create my demo database. You see, it's always the same. And now I insert 3 million rows into it. These 3 million rows are now orders coming from the year 2000 up to 2019. So I again create my partition function here. And this is something what you really need here when you want to cover your SLA. You have to have multiple file groups, otherwise that won't work. And again, there's one important point. My database, my demo database, and data warehouses will work the same. Oh gosh. Look to this, it's running in simple recovery mode, okay? So that's a small difference here, how to restore, very small. So then I create my partition schema based on the partition function. Here it is. This is my partition schema. And now I rebuild my table, pushing the data onto this partition function, onto these partitions. Now we have this situation. So every single partition here contains approximately 60,000 rows. Look to this, we have 11 megabyte of data. It could be 11 gigabyte or 1 terabyte, for example. It doesn't matter. But the key point here is that I now have every single year in a separate partition. And when I go down, you'll see this one here. And here our business immediately increased. Oh my gosh. You see that we have here 500,000 orders, 499, and so on. So the last 4 years were really good business. So the point for the business now is when they run analytics, they just, let's say, want to only have analytics about for the last 3 years, but not over 20 years. To be honest, that doesn't make sense. What you sold in 20 years, for me especially, it's out of interest. Everything what's older than 10 years, in my scenario, in my personal scenario, is not a thing what I want to have. But how can you now help the business and yourself to cover your SLA, your service level agreement? What is the key point here? Well, there is one thing what you have to do if your database is running in a simple recovery model. The partitions, what you don't need anymore here, let's say they get never ever updated again, mark them as, oh, come on, wrong key, mark them as read only. Then, so I do this, it goes very fast. And now you see that the year 2000 is closed, 2001 is closed, and so on and so on. But only the last 2 years are here read write. That means that we could insert data. So what will happen now is the following. I make a backup of the database, as you hopefully do every single night. Or someone said, well, backup is for cowards. I would say, yeah, can be. So I drop my database, and now I restore my database. Let's see how long it will take. And this is a full backup, a full restore. Yeah, okay. You see that it was taking 2 seconds, but this database, to be honest, it's only a few megabytes in size. We had a situation at a customer that was back in 2010, I think, and we had to restore a 2.5 terabyte SharePoint database. It was taking over 6 hours, and that was a pure nightmare there. So think about this. Let's say my database will take 2 days and let's say, yeah, 72 minutes, because it's way bigger. So what can we do then? 2 seconds ought to beat. And here comes the cool point. The only thing what you will do first, and think about the SLA of your customer. Your customer is telling you, give us back the hot data. And you do. Done. Yeah. So now what's going on here is a very interesting thing when I refresh it. Here is my demo database. And let's see whether I can access it. What I'm looking for is, so what I'm looking for is this one. So you see the database, and now think about your online shop. The good thing is that you can definitely push data into it, because here the 2018 and the 2019, they are online, and if there should be inserted anything, it will work. The point is that these partitions here cannot be accessed because they are in recovery pending status. That's okay so far. So let's try it. I want to see data from 2019, and it works perfect. Everything is working. Let's see what the execution. Okay, well, it doesn't make sense here so far. It's okay. And the predicate, yeah, okay. That's fine. But what about this kind of query? The problem here is that we have partitioning based on the key order date. So if I run a query against the customer ID, it won't run, because the problem is that SQL Server needs to scan through all of your partitions, and that won't work. You have to use the partition key on every single query. Otherwise, it will not work. If I do it this one here, like this, then it will run. It's working. I can run an update on it. Yeah, so it worked because I'm using my partition key, and this partition is online. And here comes a very cool thing. And now think as in your role as a DBA, the only thing what you need to do is run this script here, which is going step by step through every single file group, and then we restore it. So in the meantime, while it's running this process here, you see it gets processed. You can go to the kitchen, put in your coffee, and you're completely relaxed, because now you know whether it takes, how long it will take. It doesn't matter. It's not important, because the SLA for your customer is working. It is, oh, why takes it so long? Your customer is running the queries on the hot data. That is the SLA, and you fulfilled it. So now when everything is done, and now your database is online. Oh, that is just only. Go for this. What? Oh, yeah, typos. Effect fingers pressing small keys. So now you see everything good. One is online, and you're happy again, and your customer is happy the same way. So there is something in the chat. 5 more minutes. Okay, there are questions also. Then I would say we just stop here. You can replay it by yourself, and I would be happy to answer questions then the next 5 minutes.
Okay, perfect, Uwe. Is this the end of your session then? Shall I take the questions for you?
Yes, please.
Okay, so the first question, let me just scroll down, is okay, similar. Okay, Terry has. So the first question is from Terry. It says it was some time back once you had started Uwe. So it says, interestingly, I've seen a similar use case for telecom companies capturing call data from switches.
You mean the switch operation? Is it that what you mean?
Yeah, this comment came at about an hour back.
I know. Yeah, that's exactly the same. Yeah. And yeah, you mean the first demo with the pharmaceutical industry? And yes, that can work the same way with any business, really any business, where you have hundreds of thousands of processes who want to write into your database. That will speed up your write processes. And the switches, I think that is the switches in the network infrastructure. Did I understand this correct?
Yeah. Yes, Terry, hopefully we understood your comment or question correctly. In case if you have any further comment, please use the chat window. Srinivas has a question. It came, Uvi, it came sometime in the middle of your session, which is, have you tried memory OLTP? I think it's in-memory OLTP without lockings.
That's a good thing. Yeah, in-memory OLTP, that would be a good choice too. Yes. But think about this: if you have in-memory OLTP, then you have to store the data again on your storage. And what about if the tables are too big for this? So one of my customers, the biggest machine I've seen so far with a customer is a 4 terabyte memory. But what about if your table, and this is our very small things here, but what about if your table is, let's say, 1.5 terabyte? It could work, yes. And I think it's a practical solution, but I would definitely not do it with big tables.
Okay, so Terry has confirmed, yes, he was talking about network switches.
Perfect, yeah.
Okay. Well, Uvi, that finishes the questions for the time being. Would you, okay, we have another one that says, can you bring back the slide with links from the beginning of the presentation? Probably.
Absolutely, for sure. Okay. Yes. You mean this one, yeah?
Yeah, I guess this one. So, Dejan, feel free to take a screenshot of that.
Yeah, one information, take care of the upper lower cases for the slide decks, please. This is a bit.ly link, and I didn't know when I created it.
Uvi, can you copy paste these links into the Zoom chat window, and I'll transfer them to the chat here.
Oh yeah, that's way easier. You see, sometimes you see a 30 years experienced old guy, and then he doesn't come to the easiest thing. I push it here. So this is the link for everybody to the slide deck. And this slide deck then contains the links for the databases. Okay, so here for the audience, here is the link to the slide decks there in the chat window, friends. And once you get access to the slides, you will get access to all the links there in the slide. Yes. Okay, one more question comes up, Uvi, from Praveen. For a large table, let's say 10 million plus rows, should we have partition to improve select query performance? That is a cool thing. Amit, can you please give me 5 more minutes to demonstrate exactly this problem? Yes, of course. Oh, thank you. Because yeah, this is one of my topics here. And my biggest thank you goes to Itzik Ben-Gar because he showed the trick. So the question is, can partitioning improve the speed of the query if you run a select statement on this? The question is, it depends. But let me check this. Query performance issues. I had exactly this situation with a database of 4 terabyte of size, and we were running into a problem, and we couldn't understand what's going on here. So I run quite quickly through it because I think the session gets recorded so everybody can play around with this afterwards. So here is my table customer orders, and I insert 3 million rows in it. And then I partition my 3 million rows. I'm pushing the data, that goes quite quick here, on a partition. So that does mean that now every single year again, has the data in its own partition. But here comes the problem, and this is something what Praveen, I think, mean. You can improve the query if you always use the partition key in your query. So for example, it does mean here we are using it on the order date. So to improve it, you have to have the order date in your query. But what happens for this? You see here, I want to have the last order number. And when I look into this execution plan, you will see SQL Server is using a full scan on the custom order. That's, by the way, is okay because we do not have an index on the order number. And here comes the point, and I was really thinking, what's going on here? I create an index as expected, and we are all experienced developers. I would definitely say, well, fantastic. SQL Server will now use this, this index, and I get the max ID. And it should be quite fast. You look to the execution plan. Whoops. You don't see a seek here. I would expect a seek on it, but it doesn't. And the reason why it doesn't is here, when you look to the partition, it says it's true. And the actual partition count, so what is SQL Server scanning in, is 21. So all my partitions, look to the IO. Oh my goodness. Oh my goodness. So absolutely not a really performant query. And the second thing, what is really bad, is that SQL Server is consuming, in my scenario here, 8 cores. It's going through 3 million rows, and it's consuming 8 cores. So what can we do? Here comes the trick. Let's say, so this is a partition function, the $partition, that something you unfortunately have to look into the documents. What I'm doing is give me, in this query, from the partition number 19, from every data which is in the partition number 19, the maximum order number. I run this query. Oh, that was fast. When I look into this, I see in scan, but please, all watching this here, do not think, well, oh my goodness, it's an index scan. No, it's an operator. But what SQL Server is doing, it stopped the scanning immediately after the first row has been received, and the index scan is reverted, so it's descending. So what will happen? SQL Server will get the biggest value, and it stops immediately after the first. And here is the proof by evidence: 3 IOs. But that will not solve our problem, because I want to have the maximum number over everything, but not only over the partition. But here, a more experienced developer will immediately see what you can do with this. Look to this query. What I'm doing here is I'm creating a CTE and say, give me every partition number, only the partition number, for every partition of my index. I know it's hard-coded and it's not best practice, but in this scenario, for better understanding. You see that I know when I run this query, only this one, I get 21 rows, partition number 1, 2, 3, 4, and so on. This partition number gets returned from this CTE. And the only thing what I then have to do, I have to do a cross apply from the PN from my CTE, 1, 2, 3, 4, and pushing into the cross apply the partition number. And when I run this query, it's incredible fast, but look to this. We are not going in parallel. We have to walk through all partitions, really. That cannot be stopped, but look to this. Hey, come on. This is a success, isn't it? And that's something what you have to think about when you're dealing with partitions. Aggregations over partitions over a single partition is great, but if you're doing aggregation over all the partitions, then it might be that you will suffer from extreme performance problems. That will help you. So if you want to figure it out, try it out by yourself, hit the script number 150. And I hope that you will then enjoy this speed up in this query. And maybe I helped you here with a few problems with your partition.